Hi, I'm Fabio Ottaviani, creative developer at Studio Gusto. I welcome you to the Awards Academy's class. Before getting straight to the point, you will unfortunately have to listen to some words about me. I'm sorry, but it's a bundle. In general, the classic dating apps boomer bio, I like art, photography and music, tragically suits me. So I'll try to be more specific. My personal pursuit of happiness gets me digging in the underground scene and in different landscapes quite far away from the mainstream. I try to channel this energy into my work to reach a spiritual balance, mixing bold elements and elegant dynamics, often very playful. I use this word because my encounter with design has opened the doors of my amusement park, a private and constantly evolving space with merry-go-rounds to share and roller coasters I keep for myself and my mental health. I turn all this passion into a complete devotion to the altar of coding and collected years of sleepless nights only to keep learning. Thanks to Studio Gusto and to Awards Academy, I will open the doors of my playground. And I really hope you will have fun. I'd like you to go through this lesson and its apparently snooty title, knowing that it is one possible road among many others to step into a world that is vast and beautiful. Amazing artists and developers create new paths and ways to walk them on a daily basis. I just hope to convey the joy in finding your own ones. In order to talk about the path we follow at Studio Gusto, I want to show you the process that led us to the creation of our Gusto Play 2. It is a web experience that involved the hands and minds of many colleagues in our team, and that is where we will find the juicy part you are all here for. Gusto Play 2 was born from the will of creating a live and engaging project, able to entertain us during the first lockdown, when getting outside our doors was not an option. The only thing we could do was get out of the box. I worked on the particles 3D animation. Let's find out how. Hi! If you go to github.com/studiogustodev/3d-particles, you will find the files to start with this course. You can clone the repository with Git or by downloading the zip file. There are some minimum requirements to start the course. The first is that you have installed Node.js on your machine. If you haven't installed Node yet, go to nodejs.org and download the recommended version. For those who don't know, Node.js is a JavaScript runtime that allows us to write server-side JavaScript applications. If you have already installed Node on your machine, you can check its version by going to the terminal and typing node-v. Check that the Node version is equal to or higher than 10. Also check the version of npm, which must be equal to or higher than 6. However, if you unfortunately have installation problems with Node, you will find a link in the repository that will help you to overcome this problem. Another key requirement for this course is that you have Blender installed on your machine. Blender is a free 3D software that will allow us to create or edit 3D models to be able to export them correctly for Three.js. Be sure you download the latest version to follow the tutorial on the Blender's part correctly. This course obviously requires a minimum of knowledge of the Three.js library. So, if you are still a beginner, I recommend you to take a tour of a couple of fundamental guides. The first, of course, is the Three.js documentation. Here you will find everything you need to create everything that I will teach you during the course. The second guide is 3GS Fundamentals, which will give you the right basis to start entering the WebGL's world through 3GS. Well, let's start. Once you've downloaded the repository, open it in your favorite editor. Mine, obviously, it's Visual Studio Code. Within the repository, we have a folder called Materials, which will contain two folders, Horse and Skull. Here we will find the 3D files that will be useful for our course. Later, I will tell you where I found these resources. Inside the source folder, we have a very simple index.html with the inclusion of an index.js script and the inclusion of a stylesheet style.css. These two files will contain the starting code of our tutorial. In index.js, you will find a basic example of 3JS that will serve as a starter. And on style CSS, you will find just few rules to position the canvas inside the body. In the static folder, you will find another folder called Draco. Here, there are two fundamental files to be able to import the models that we will export from Blender via Draco compression. In package.json, we will find all the dependencies that I used for this project. Obviously, there are 3JS and GZAP, which, as we will see later, we will need to animate the particles. We will be using Parcel to serve our app into localhost and Parcel plugin static files copy. This plugin allows us to copy files inside the static folder directly to the dist folder during development and after the build. Parcel will do this step for us automatically. Now let's create a new folder inside static called models. Here we will have the 3D files exported by Blender. Now we can install our dependencies. Visual Studio Code has a very handy built-in terminal that I love to use to keep everything under control during development. So let's type to the terminal npm install to install our dependencies. Once all dependencies have been installed, they will be present inside the Node Modules folder. Our package.json has two scripts, start and build. Start will allow us, via Parcel, to start our localhost server on port 8080. Build will allow us to create a package with the whole distribution ready to be uploaded to development server. Now let's type npm run start to start our server. Once the application is started, a new browser window will open at localhost 8080. Let's go take a look inside. Open index.js. I have imported the 3JS module and Orbit Controls. Orbit Controls is a 3JS module that will allow us to navigate within our 3JS scene with the mouse. By dragging, we can rotate the camera, and with the mouse wheel we can zoom in and out. I have already set up a 3JS basic boilerplate. We have a WebGL renderer with anti-alias true and alpha true. I set its size equal to the width and height of the window, and added the canvas inside the document body. Then there is a scene and the camera with a depth of field at 50. its position on the axis at 5 units and the Y position at 1, just to see everything from above. Also, I have added a cube, a mesh with a box geometry and a green mesh basic material. Obviously, I started orbit controls and I added two helpers, grid helper and axis helper, just because axis will allow us better understand what we will do. Y-axis will be the vertical one, x-axis the horizontal one, and z-axis the depth one. Obviously, to start the render, we need a function that I called animate. Through request animation frame, it will call itself and the renderer will be able to render everything that the camera will see in the scene. I've also added a resize function that will ensure that when we resize the browser, the canvas will always have the same size as the browser window. Perfect! This is our starter kit. Now we will move on to Blender to start working on our 3D models. First of all, the title we chose emphasizes our will to create particles with bad 3D models, but they won't be that bad. The models we are going to download are indeed good and designed by professionals. What is actually bad is the compatibility for the 3JS world, so we are basically going to improve their performance. We will manipulate and optimize them, so that once exported, they will be as fast and light in order to achieve our goal. To do so, we'll use Blender, a free open source 3D software that will allow you to model, animate and compose three-dimensional images. It offers a wide variety of features to create incredible renderings that are in no way inferior to its big competitors, like Unity, Cinema 4D, 3D Studio Max or Maya. We chose Blender because it is a free software, available for all platforms, and it also has a very active community you can always rely on for further information or tutorials of any kind. So, if you still haven't, download now the latest version of Blender. Where can you find free resources for your 3Ds? Let's start by searching on Google 3D Model Free. As you can see, we have a lot of results. Personally, for our course, I chose free3d.com. This site is full of 3D models free or for sale. Let's find a school. I chose to download the first resource, which with almost 80,000 downloads, it is one of the most popular. Before downloading the model, always check if there is a license that allows us to use it. I also decided to use a horse model. Actually, we will only need its head, but all the interesting heads were for sale. So I downloaded a full horse and then we will separate its head. By the way, you don't need to download these resources because I have already done for you. You can find them inside the Materials folder. Once you open Blender, you will find this easy-to-understand interface. In the central part, we have the viewport, and every time you will open Blender or create a new file, it will have a cube a camera and the light. For this project, we don't need the camera and the light, so we can go to the right panel, Scene Collection, and click on the eye icon to turn them off. We will keep the cube visible, at least for now, because we will use it as a placeholder to understand the size of the files we are going to import. In fact, we will scale our models based on the size of the cube, because once we import them into Three.js, we won't need to rescale them and the processor will do less computation. So, since we can do it directly in Blender, we take advantage of it. Let's start by importing our skull. Click on File, Import, Wavefront OBJ, just because the extension of our file was in OBJ format. Go on Materials folder, Skull, and select it. First thing we notice is that it is very big compared to the cube. Let's try to understand how to move inside the Blender viewport. If you have a mouse with a middle button, scrolling up and down will zoom the viewport. Instead, keeping it pressed, you will rotate around the origin. For lateral panning left and right, up and down, just hold down the Shift key on the keyboard. If on the other hand you have a magic mouse or trackpad, like me, to zoom you have to scroll by pressing the Command key. To rotate around the orbit, just scroll. Now look at the axes. They are different from those of the Three.js environment. In fact, while on Three.js we have the vertical axis, which is the y-axis, here on Blender this axis corresponds to the z, while the depth axis is the y-axis. So they are reversed. But don't worry, Blender will automatically reverse the axis for us upon export. We will see it shortly. Now let's take care of resizing our skull. Click on it. Look at this right panel, Object Properties. Its x-axis is rotated 90 degrees. Click and set the value to 0, so the skull looks towards us. Now we want to center the whole skull on the origin 0, 0, 0, but we notice that location X, Y and Z are already centered. Then right-click on the skull and set the origin to the center of its mesh. Now we want to center it on the origin 0, 0, 0. We set the value of X, Y and Z to 0, so the skull will center itself. Now we need to resize it approximately like the size of our cube. To do this, move to the top right of the viewport in this shading panel and click on the wireframe view. Now we can see everything in wireframe mode. We can scale our object by going to the Object Properties panel and setting the X, Y and Z scale values to 0.5, for example. But it is not enough to reach the size of our cube. To speed up this step, we can click the S key on the keyboard and move the mouse to the center. So we have more control in scaling our skull. Let's try to insert it inside the cube. Even if this part will remain outside, we can try to center by clicking on the Move icon on the left panel and move the green axis to the right, that is the y-axis. Once our skull is more or less centered, we can proceed with the optimization of its geometries. Let's turn off the cube by clicking on its eye icon on the Scene Collection panel. Now let's rename the level of our school. Double-click and let's type school. If we click on the side arrow, we can see that our model is composed by a geometry and a material. Click again on the side arrow and we see that there is a material. To see it, click on the material preview icon in the shading viewport panel. In fact, our skull already had an image as a texture. We can find it inside the 3D Particles Master, Materials, Skull, Skull.jpg. Since we won't need it in Three.js and since we want to keep our model as light as possible, we can right-click on the material and then delete. While we are here, let's rename the geometry too. Double-click and type skull. Click again on the skull and go back to wireframe mode. We can see that our skull has a lot of vertices and we won't need them all because we want to stay super light. Later, in Three.js, we will deal with inserting particles over its entire surface. For now, we can decimate all its vertices. To see the number of vertices of an object, we only need to switch on the object we want on the Scene Collection panel. Then, on the status bar, if you don't see this information, you can right-click and activate Scene Statistics. Now you see that all the objects within the scene, so just the skull, contain 40,062 vertices, and we obviously want to decrease them. To do this, we will use a Blender modifier. Let's move to the Modifier Properties panel by clicking on the wrench icon. Click on Add Modifier. Here we find many modifiers, but the one we want to use is Decimate. We have an input ratio. If we move its value towards 0, dragging to the left, we notice that the number of vertices of the geometry decreases. Now we want to get a shape that has enough vertices not to destroy the skull shape. By the way, it has to be light. To do all things the same way, we can set the value to 0.05. Very good. A key thing before exporting the file is to go to the Object panel and apply all the object transformations we have done so far. So, Object, Apply, All Transforms. Once we import our object into Three.js, we will see the size of the object exactly as well as in Blender. Now we just have to export the file. Click on File, Export, GLTF 2.0. Go to our project folder and click on the static folder. If you haven't done it in the previous chapter, create a folder called Models, enter it, and rename the file to skull.glb. Be sure you have selected the GLB format. The GLTF format contains a 3D model saved in GL transmission format. This format stores a complete description of the scene in JSON format, which includes a hierarchy of nodes, including cameras, lights, materials, and meshes. The GLB format is always like a GLTF format, but in a binary version, therefore lighter. Click on the Remember Export Settings checkbox so we will be fine when we will export the horse. Expand the Include tab and click on Limit to Selected Objects. So let's remember to have only the skull selected in our scene, or it will export everything that has been selected. Click on Transform. As I told you before, this checkbox Y up must be active so that Blender reverses the Y and Z axis. Open Geometry panel, click on Apply Modifiers to apply the Decimate modifier we gave to the skull. Here we leave everything exactly as it is. And now we can activate the compression. Since Blender has already integrated the compression with Draco, we use this panel to compress our files. Keep compression level at 6 and all other parameters as they are. Also, open the animation panel and disable the animation ticks. Now we have just to click on Export GLTF to export our skull. Let's see what its size is. Enter on Model folder, Skull, and we see that this file is only 28 kilobytes. Definitely much less than its texture image, which is 161 kilobytes. So we went from 6.2 megabytes from an OBJ format to 28 kilobytes of a GLB format. Awesome! And now it's horse time. Let's turn off the skull and turn on the cube that we will use as a placeholder. File, Import, Wavefront OBJ, and let's select the horse in the horse folder. We don't see it in the scene because the horse is actually very big. Come back to the Object Properties panel, click on the horse. It has a 90 degrees rotation on x-axis, so set its value to 0. Let's try to scale the horse quite similar to the size of the cube. Press S key from the keyboard and move the mouse closer to the origin to zoom out. As we did it for the skull before, right-click and set its origin to the center of its mass. We can now set location X, Y, and Z to 0 to center the horse within the viewport. Now, what we really want is to have only the horse's head, not the whole horse. So, we create a Boolean operation to extrapolate its head. To do this, click on the Add menu, Mesh, and then UV sphere. We just create a sphere that we will now move under the horse's head. Select Move Tool on the left panel and be sure to have the sphere selected. Then we move it on Y-axis and then on the Z-axis. Obviously, based on how much you have scaled the horse, try to make the sphere larger or smaller. S key on the keyboard and let's try to intersect until this point of the neck. And rotate the scene to verify that the horse's head is inside the sphere. Now, still with the sphere selected, we can add a new modifier. Click on the Modifier Properties tab and Add the Boolean modifier. Click on the object input and select American Horse. Then click on Intersects tab to create a Boolean between the sphere and the horse. Go to the arrow next to the small camera and click Apply to apply the transformation. Now the sphere has become the horse's head. So, at this point, we can turn off the horse from the Scene Collections panel. Double-click on sphere to rename into horse. Check its content and see that it contains only one geometry and no materials. Back to Object Properties, click on the horse's head and set the origin at the center of its mass. Right-click, Set Origin, Origin to Center of Mass. Now we can set its location X, Y, and Z to 0 to center it. As key again to scale it inside of the cube, more or less. You can also move it slightly, but it is not important that this operation is precise. We can be satisfied with this result. Now that we have scaled everything, we can also turn off the cube because we won't need it anymore. Like we did for the skull, we can reduce the number of its vertices. Let's go back to the Modifier Properties panel and add the Decimate filter. Now let's lower the value of the input ratio to decimate the vertices. Remember, we always try to keep clear the shape of the horse using few vertices as possible. Let's set this value to 0.03 to stay aligned altogether. We can click on the solid view to verify if its shape is okay. Now let's click on the horse and remember to apply all the transformations before exporting. Object, Apply, All Transforms. Finally, we could export it. File, Export, GLTF. We should have checked Remember Export Settings. Also check that the horse is the only object selected in the scene. Fact check that all our settings are correct and rename file in horse.glb and save it in the static folder Models. Let's see its size. Okay guys, our horse went from 13.4 megabytes to only 6 kilobytes. Incredible! I'm quite happy about this. Now we have to import everything into Three.js and turn these models into thousands of particles. Are you ready? Now we can import our models horse.glb and skull.glb inside our Three.js scene. To do this, we create a new file inside the source folder, which will be called model.js. In here, we will create a class that will manage our 3D models until they are converted into particles. So, let's create a class which will be called model. It will have a constructor with an object as a parameter. Let's do a console log of this object to see what it will contain. And export our class. Back to index.js. Import our model class that we just created. Now let's create a models section just below the helpers. Add a new model instance for the skull. As a parameter, it will have an object with its name, skull, and a file that will contain its location. Obviously, we don't have to worry about not having inserted the static folder in the path, because everything inside the static folder will be copied directly into the dist folder. This is done by Parcel thanks to this plugin, Parcel plugin static files copy. So don't worry. Let's add a model instance also for the horse. Save and back to terminal to restart our server if it was stopped. npm run start. Now, in the console, we have the log of our two objects, skull with its name and file, and horse. Back to model.js. Let's add these parameters to the this keyword. This.name equal to object.name. This.file equal to object.file. Now let's create a function called init that will take care of uploading our files. To load these two files, we need a 3JS utility called gltf loader. So let's go into the 3JS documentation and look for gltf loader to understand how it works. OK, as you can see, there is also the possibility to load files compressed with Draco. Back inside model.js and import these two loaders from the 3JS library. Hint: if you don't know exactly where the file location is, just go to the bottom of the documentation page and click on Source. This will be the path where we will find the file inside the Node Modules folder. 3. Examples JSM loaders gltf loaders. Since we are here, we can see that the Draco loader file also exists in this folder. And we needed to unpack our models. Just take a look at the example in the documentation. We need to create a new gltf loader and a new Draco loader. Draco loader needs to set the path where it can find the two files I told you about earlier, Draco decoder wasm and Draco wasm wrapper. Then gltf loader will be able to set Draco loader to load our models. Let's add all the loaders inside our constructor. Obviously, the path will be inside the Draco folder. These two files are actually always found inside the 3JS code, and you can find them inside the examples directory. JS, libs, Draco. Here we will find Draco decoder WASM and Draco WASM wrapper. Obviously, we should copy these two files and put them inside a public folder of our application. This is because once we build the project, Draco Loader will go to retrieve these files that it needs to be able to decompress and load our 3D models. Last step, we need to set Draco Loader to our GLTF loader. Now, inside the init function, we can load our files. This loader load this file. Here, we'll have a callback function with the passed response content. Let's do a console log of response and comment on console log obj. Save. Very well. We managed to load our two files. Let's analyze them. Explode, scene, and explode children to get an array. In this array will be the elements we exported from Blender. Here there are the meshes of our models. And here we have horse. And in here we will obviously have the skull mesh. Perfect. Inside each mesh we have a geometry, which is a buffer geometry with attributes: normal, position, and UV. What we will be interested in will be the position attribute, as we will see shortly. But first, let's insert our objects into the scene. So, as we have seen, let's add a new property, this.mesh, equal to response.scene.children index 0. And because we want to import into the scene, we need the scene. So let's back to index.js, and inside each model we add a new property called scene that will be equal to our 3JS scene. And it's where we are putting our files. Same thing for horse. Back to model.js and add this scene equal to object.scene. Finally, we could add this mesh inside this scene. Here they are. We see them black because the mesh material is a mesh standard material and we have no lights inside the scene to see them. Let's change the material with something easy. This material equal to new 3 mesh basic material and change its color to red. Remember that we need to import 3JS into the file in order to use mesh basic material and all the other 3 properties that we will use. Now we can replace this mesh material with our new material. And save it. Now we have our models fully red. Let's add wireframe to true to see it better. Perfect. Let's comment the cube from the scene for a moment. OK. Now we can comment the horse to see only the skull. And comment the skull to see only the horse. OK, now let's create 2 buttons to add or remove the 2 models from the scene. Open index.html. I will create a new div with ID controllers, and inside we insert 2 buttons with class button and the name of each model, school, and horse. Very well. Let's go inside Style CSS to make them beautiful. Controllers, position fixed, the index 1, left 0, top 0, text align center, width 100%, padding 10 pixels. Now class button, border none, background white, color black, padding 8 pixel, 20 pixel, border radius 15 pixel, cursor pointer, outline none, margin 5 pixel, and font family sans serif. Finished! Now, when we click on the skull, only the skull will be displayed. And when we will click on the horse button, we will see only the horse. Back to index.js to decomment our skull. In model.js, we add 2 new functions, which will be add and remove. Into add, we are going to insert our model into the scene, and in remove function, we will remove it. Back again to index.js, and under models, we create a new block which will be called controllers. Here, I create a buttons variable which will be a query selector all of all buttons with class button inside index.html. We will obviously have an array as a result. So buttons index 0 will be the skull button, and to index 1 will be the horse button. For each of them, I will add an add event listener to the click event, which will create a function that will allow us to add the skull and remove the horse. Same thing I do for buttons index 1, which will be the horse button. Obviously, here, when we click, we will remove the skull from the scene and add the horse. Save it. Now, clicking on the buttons, we see in the scene only the respective model. Perfect. The only problem now is that if we refresh the page, neither model is inside the scene. So, to view the skull as soon as it is loaded, let's add a new property to the skull instance. Place on load equal to true. Now, inside model.js, in the init function, we are going to put a condition. If this place on load is equal to true, we can call this add to insert the model into the scene. Remember to add this place on load to the constructor. Save it. OK, now, whenever we refresh the page, once the skull model has loaded, it will automatically be added to the scene. Every single intersection of the wireframe corresponds to every single vertex with x, y, and z coordinates. We could add our particles in every single vertex. And for this, we can use the points class of Three.js, which allows us to render points instead of vertices. Let's clean up our code first. Remove this console log and create comment blocks that will give a clearer look to the code. Here we have the material of the mesh. And let's add the mesh geometry to this geometry, which will be equal to this mesh geometry. I had a comment block here for place on load as well. Now let's create our particles. These dot particles will be a new 3 points. And just like mesh, it will have two parameters, a geometry and a material. We have geometry, and at this point, in the add and remove functions, instead of displaying this mesh, we will put these particles. Here are our particles that have positioned themselves exactly above every vertex of our geometry. I'm not satisfied. There is in fact a material made on purpose for the points object called points material. Let's look for it in the documentation. As you can see, points material allows us to add a size parameter to manage the particle size. So, we create a new material which will be called this.particles material. red colors for the particles, and add a size, for now quite small, let's set it to 0.1. Now let's replace the material in these dot particles. The result is obviously not the best. Let's decrease the particle size value to 0.05. And we also comment our helpers on index.js to look better. First of all, the back of the skull has few vertices, while we have a lot of them on the teeth, cheekbones and nose. The horse, on the other hand, has a better uniformity of points. Now we want to get thousands of particles that are positioned in a balanced way over the entire surface of the models. And to do this, we will create a new geometry from scratch, and it will contain a new attribute position with all these vertices. To make you better understand what we are going to do, let's do a console log of the current geometry. Let's go to model.js under this geometry. Perfect! The object type of our geometry is buffer geometry. What is a buffer geometry? Let's look for it in the documentation. The geometry buffer is a representation of meshes, lines or points. It includes vertices, face indices, normals, colors, UVs, and custom attributes. A buffer geometry also allows us to pass data to the GPU much faster thanks to buffer attributes. As you can see from the example, to create a buffer geometry from scratch, which contains the vertices of a simple square, you create a new float 32 array and insert all the positions of the vertices one behind the other. Each point is a position x, y, and z. Finally, to insert the attribute inside the geometry, we need to use the setAttribute method, which will contain the name of the attribute we want to create, and a buffer attribute, which will contain our float32 array, and the second parameter, which corresponds to the number that should be associated with the type of data. In this case, since we are putting vertices with 3 positions, we have 3. Let's check the console log of our geometry. We can see that the item size of each float32 array stored the number corresponds to the type of data, that is 3, because positions are vector 3. UV, on the other hand, which contains the information to manage the textures, has only an item size of 2, because the positions that are used to map the image for a possible texture are only vector 2. Now let's think about filling this surface with particles. To do this, we will be helped by a utility class available in Three.js code. Its name is Mesh Surface Sampler. This utility allows us to create vertices randomly distributed over the entire surface of the mesh. We then import the Mesh Surface Sampler module inside model.js, and we find it inside examples JSM math. Then, as in the example, let's create a new sampler variable, which will be a new mesh surface sampler, and it will accept a parameter that is our original mesh. Let's create a new section which we call Particles Geometry. Our original mesh will obviously be this dot mesh. We can already add the build method, which will start thinking about how to randomly distribute the vertices inside the surface. Then we decide the number of particles we want. For now, let's do 10,000. Then we will change this variable according to the result we want to obtain. Now let's create this dot particles geometry, which will be a buffer geometry. We need to create a new float32 array, which we will call particles position. Another peculiarity of the float32 array is that it needs to know how many values it should contain, because, as we have seen previously, it will also serve the buffer attribute to know how much the array will be divided. In our case, its size will be the number of particles multiplied by 3, because each vertex will contain x, y, and z, and each number will be contained in its corresponding array index. Then num particles will be multiplied by 3, so that we can hold 30,000 positions, which divided by 3 will give us 10,000 vertices. Now we can create a loop to fill particles position. Here we need to create a vector 3, which we will use into the mesh surface sampler function to build its positions. This function is called sample. Sample accepts as a parameter a target position, which will be our empty vector 3. Let's create a new variable, new position, which will be a 3 vector 3. Now we can add a new position to the sample method. A float32 array has a method called set, which allows us to insert the contents of the new position vector. We must also specify how many positions we are inserting each time in the array. In our case, inside the loop, it will be index I multiplied by 3, because obviously we are going to insert 3 new numbers every 3 times index. Particles position set a new array with new position x, new position y, and new position z. Here, after the end of the array, we go to insert y times 3. To make you understand better, when the index is 0, we are going to insert new position x at index 0, new position y at index 1, and new position z at index 2. When the I is 1, 1 multiplied by 3 is equal to 3, and then consequently new position y will go to index 4 and new position z at index 5, and so on. After the loop, we can finally add new position attribute to our this.particles geometry. There is a buffer geometry method called setAttribute, which will accept the name of the parameter we want to create, which will be position. And it will accept another parameter, which will be a new 3 buffer attribute, which will contain our float32 array particles position. And it will need to know its item size, which will be 3. I hope everything is clear. Well, now let's do a console log of this particles geometry to see if everything is okay. Oops, guys, I made a typo. I wrote 3 buffer geometry instead of 3 buffer geometry. Let's go to line 62 and correct. Let's comment out the old console log of this geometry on line 45. Okay, now let's see this particles geometry, which is a new buffer geometry, which contains a position attribute which will contain 10,000 new vertices, which are 30,000 new x, y, and z positions. Are you ready to see the result? Let's go to replace the geometry of these particles. In this dot particles, instead of this dot geometry, we replace this dot particles geometry and save. Wow! We finally managed to get 10,000 particles. We started with very light models that didn't even have 10,000 vertices. This mesh surface sampler function is fantastic. Imagine if we had to export a model with 10,000 vertices or more from Blender. Its weight would have been considerably greater, and we probably would not have been able to obtain such a uniform distribution of vertices like this way. At this point, we can also decrease the size of point materials to 0.02 and increase the number of particles. Instead of 10,000s, let's add 20,000s. Incredible! We are definitely on the right track. Now, guys, we just have to start coloring and animating our particles by starting to play with the shaders. Three.js has a lot of available materials, but if we really want to go for it and create special colors or apply distortion to the geometry, we would have to use lights, textures, and edit vertices positions on the render in real time. And all these would dramatically lower the performance of our creations. Fortunately, there is a material called shader material that allows us to edit colors and vertices directly via the GPU, so we can leave the CPU processor free, because the graphics card can make calculation way faster and in parallel. Therefore, Three.js is basically a library in charge of translating each written JavaScript line of code into GLSL language. So, every material we use inside the library is just a set of GLSL programs, of which some are complex and others not. Due to time and to avoid boring explanations that would last forever, I will try to condense some steps of this class in the shortest way possible. You can still go deep into the details of all the information I will give you by simply getting to these two websites, which have been fundamental for me, and will do the same for you if you want to go further along this route. The first one is WebGL Fundamentals. Here you will find out exactly how WebGL language works, from the very basics to 3D. Basically a ticket for Three.js Backstage. The second one is the Book of Shaders, a step-by-step guide that will take you on a journey of the fragment shaders world. I can assure you that the more time you will spend inside of it, the clearer and simpler things will look. Just take your time, and you will start to create more complex elements day after day. Okay guys, at this point it's time to replace material. We will no longer use points material, but we will create a new shader material. Meanwhile, let's comment points material and recreate this dot particles material, which will be equal to new 3 dot shader material. First, shader material is composed by two types of shaders. One which is called vertex shader and one called fragment shader. The vertex shader, as you can guess, takes care of managing the positions of our vertices. Instead, the fragment shader is used to color each pixel of the mesh. Let's create two new files inside a new folder which we will call shader. These two files will be vertexshader.glsl and fragmentshader.glsl. And let's import them into model.js. I import them with the name of vertex and fragment. And let's add them to our material. Vertex shader will be equal to vertex, fragment shader equal to fragment. Now, to speed up the writing of the GLSL code and make it less painful for you, I decided to put two snippets inside the repository. You can copy and paste the code into their respective files. Inside Vertex Shader, we will insert the Vertex Shader sample snippet, and inside the Fragment Shader, we insert the Fragment Shader sample snippet. Advice: to see the syntax we write inside the GLSL files correctly highlighted, we can use one of the Visual Studio Code extensions that help us to highlight the keywords. And thanks to this, we can avoid losing sight every time we write GLSL code. In Visual Studio Code, go to the Editor's Extensions panel and search for Shader Languages Support for VS Code. Click and install. Now we see that inside our files, the syntax is well highlighted. I can assure that your eyes will thank you for it. Now let's save and go see what happened. Beautiful! We have a lot of wonderful particles. Now I'll explain better what is written inside our two files. Let's start with vertexshader.glsl. This is a program written in GLSL, which is a kind of C language, which have a main function. GLPosition will be one of the two outputs of this function. At this moment, its value is the result of a series of multiplications to exactly calculate the position of each single vertex within the world of Three.js. Instead, GLPointSize contains the result of an operation that is used to resize the particles according to their distance from the camera. 8 plus 0 is the size of the particle. You can increase or decrease this value to obtain larger or smaller particles. For now, we leave it at 8.0. Don't worry if these steps aren't clear to you now. Just know that they are fundamental. There are many articles explaining exactly how local space, word space, and local space work. I don't want to bore you too much, and this speech would be too long. You can find everything in one of the resources that I linked to you in the repository, WebGL Fundamentals. Let's go back to the vertex shader. As you can see, we have position here. In reality, this position is exactly the position we have inside the attributes of our geometry. you have to know that this variable has already been automatically passed to us by Three.js via shader material. Actually, if Three.js hadn't done it for us, we would have had to import it by writing on the top of our code attribute vec3 position. But Three.js helps us in this step, assuming that the position attribute, as well as UV and normal, should be used in our material, and therefore there is no need to import them into our GLSL code. So we can comment on this import, but I leave it here for you to understand where position comes from. Please be patient if you still do not understand. Soon everything will be clearer. Let's move on the fragment shader now. In here, the output function will be glFragColor, which will be equal to a vector 4, which is nothing more than a color, RGBA, where the colors, instead of going from 0 to 255, as we are used to seeing them in the CSS or in the color pickers, go from 0 to 1. So let's try color the particles red again. Since red in RGB equals 255 for red channel, 0 for the green channel and 0 for the blue channel, we can simply put a 0 in the second and third position. Save. And now we have all our red particles. We can move this triad of RGB colors into a new variable we call color. We will write vec3 color equal to vec3 open parentheses 1.0, 0.0, 0.0 close parentheses and semicolon. Instead of this triad of values, which exactly matches this one, we can write color. Now guys, I give you 3 basic rules for GLSL programming. GLSL rule number 1. At the end of each line, we need to add a semicolon. If we don't add it, the program gives us an error. In fact, in console, it gives us error on line 92. However, it does not correspond to line 92 of the fragments shader's code. So we can scroll all the error until we see line number 92. Once we get to the line, we see that the error is not in this line, but in line 90. So when we have an error in the console, we try to find the error in the area where it is reported to us. In this case, it is here. So let's go back to our code and put the semicolon back to make the program work again. GLSL rule number 2. Any number we write, unless it is an integer, and we will not write integers in this master class, it's a float number and it always needs the point. We can use the contract version, writing 1 point or 0.0 or 0.4 zeros. In our case, for now, we leave everything in version 1.0, 0.0 and 0.0. GLSL rule number 3. Whenever we declare a variable in GLSL, we must also declare its type. Obviously, if we had a float number, we would have to write float number equal 1.0. If we had an integer number, we have to write int number int equal 1 without point. If we had to write a vector 2, we would have to write, for example, vec2 uv equal vec2 with a float number and another float number. Now that everything is clear, this data does not interest us. Another thing, once we have declared our variable, if we wanted to change its content, we no longer need to declare its type. We can then overwrite our color with a yellow, for example, color equal vec3 1.0 1.0, 0.0. To get a yellow, we need a full red channel and a full green channel. It is also possible to recall the single value of each number inside a vector 3 thanks to the syntax R, G, and B. In fact, we can write color.r equal 0.0 to get a green. In addition to RGB, we can recall any number inside vector 3 also with the classic x, y, and z. Obviously, in this case, nothing changed. So when we talk about colors, we always use R, G, and B. And when we talk about positions, such as in vertex shader, we will use the syntax x, y, and z. Now I'd like to color the particles with a gradient that goes from one color to another. To do this, we need to know the particle's position's value. The attribute position we imported, or better, that Three.js imported for us, it can be passed to the fragment shader through a particular variable called varying. Here, before the main function, we write varying vec3 vPosition. We just declared an empty variable of type varying. This variable should specify the type of data it contains, and since we want to fill them with the positions of our geometry, which are vector 3, our varying will be vec3. vPosition instead will be its name, where the letter V lowercase before position will be a letter that we use as a convention to remind us that it is a varying variable. Now we can fill vPosition with our positions. Let's go inside main and write vPosition equal position, semicolon. In this way, we have filled vPosition with the content of position, which I remind you is the position attribute of our geometry. Now, from here, we can move on to the fragment shader to retrieve the varying vPosition. We go into fragment shader, and before the main function, we write varying vec3 vPosition, semicolon. We can say that this type of varying variable is a kind of bridge between vertex shader and fragment shader, because we could not actually bring attribute position inside the fragment shader. In fact, all the attributes must be imported into the vertex shader and then passed to the fragment shader through the varying variable. Now, inside vPosition, we have all the values of the position attribute. Let's see what happens if the color value is now equal to vPosition. Color equal vPosition. Great, every time I am amazed. What exactly is going on? Let's put the helpers back for a second. Let's go back to index.js and uncomment the helpers. Then we go back to fragment shader and change color so that RGB of color corresponds only to vPosition.x, or rather the coordinates of each vector on the x-axis. Let's write vec3 vPosition.x, vPosition.x, vPosition.x and save. We can see that only the right side is illuminated. This is because, obviously, the value of the x-axis goes from a negative number to the origin, which will be 0, and will arrive at a positive number. So our color will be all black when its value is less than 0, and it will go on an increasingly clear tone until it reaches white as its values increases. When the value is greater than 1, its color will always remain white. At the contrary, below 0, it will always remain black. The same thing, obviously, happens for v position y, which will color the vertices from bottom to top. Obviously, the value of y will be negative from the origin downwards, while it will be positive from the origin upwards. The same thing happens for vposition.z, which will color the particles based on the depth of the z-axis, where the value will be positive as it approaches the camera from the origin, and will be negative in the opposite direction. So if we set the color again to vposition.x, y, and z, we can say that each axis corresponds to the coloring of the RGB channels, and as we can see, the lower part of the skull will be completely black, precisely because here there will be all the negative values of the x, y, and z positions. Now, if you wanted to color our skull with two different colors that are not black and white, we can take advantage of a GLSL function called mix. This function creates a linear interpolation between two values based on a third parameter. Let's create two new colors. Vec3 color 1 will be a red, so 1.0, 0.0, and 0.0, and vec3 color 2, which will be a yellow, so 1.0, 1.0, 0.0. Now let's use this mix function. We mix color 1 and color 2 with v position z, or rather the z-axis, which will go more or less from +1 to -1. Perfect. The function has interpolated the value ranging from 0 to 1 with color 1, which is a red, to color 2, which is a yellow. Now, if we wanted to shift the depth value so that it goes from 0 to 1, we just need to multiply v position z times 0.5 in order to obtain a value ranging from -0.5 to 0.5 and add a value of 0.5 to get a number ranging from 0 to 1. I'll show you. vposition.z times 0.5 and we get this result. But if we add 0.5 to this value, we get a value ranging from 0 to 1. Therefore, it's a good mix to interpolate color 1 and color 2. Take a look at yours. Perfect. Now we can also change the colors. If we wanted to use different colors than a full yellow or a full red, we can choose between two paths. For example, we can change the color with random numbers. Or it would be better to divide the value of an RGB by 255. In fact, let's imagine that we have an RGB that, for example, is 10, 20, and 100. We just need to divide each value by 255. The second solution instead, which is one we prefer, is to import it directly from an external variable. We will not use attribute as we did for positions. In fact, there is another type of variable called uniform. This variable can be imported into both the fragment shader and the vertex shader. We have to declare this variable inside the shader material, and we have to write it like this. Uniforms will be an object that will hold our variables. Since they are uniform variables, as you did it for the varying, let's put a u lowercase as the first letter of the variable, always by convention. So we write uColor1, which will be equal to a new object with a key value, which will be a new color. For this, we can directly use 3.color, which will translate our color into a vector 3. Let's put a random value and we also insert uColor2, which will have a new 3 color as value. And we can also insert the value in string format, for example, red. Let's go back into Fragment Shader and import the two new uniform variables under the varying. And we will write uniform vec3 because obviously the color is a RGB, uColor1, and uniform vec3 uColor2. Now in the mix function, instead of using color1 and color2, we can replace them with uColor1 and uColor2. Perfect. Obviously, both the horse and the skull now have the same colors. And to differentiate the two colors, we can pass the value of these two uniforms directly from the parameters of our models inside index.js. Let's put color1 equal to red and color2 yellow to the skull. And let's put color1 blue and color2 pink on the horse. We can go back to models.js. Add this point color1 and this point color2 to the constructor and pass this color1 and this color2 directly as our uniform values. Save. Now our skull will have a red to yellow gradient color. And our horse will have a gradient color that goes from blue to pink. Now guys, I hope it was pretty clear how we use our positions to color our models. Now we can also comment on our helpers because we won't need them anymore. So, our particles are too bright and we want to reduce their transparency. So we can act directly on the alpha channel of GL frag color vec4 and set it to 0.5. But to see the transparency, we need to activate the transparent flag in the material. Let's move into model.js and into shader material we add transparent equal true. So we can see the transparency of the particles. Now I want to give a fog effect. And so I want to make sure that the farther away the particles are from the camera, the lower their alpha gets. For this, in Fragment Shader, we can copy the value we used for the depth and we create a new variable, float depth. Its value will be vPosition.z times 0.5 plus 0.5. And we can replace depth at this point. Now we can use depth for the alpha channel and replace 0.5 with depth. Well, the depth value that goes from 1 to 0 will now be the value of the alpha, which becomes more and more transparent the farther it goes. If we wanted to make its transparency less drastic, we can multiply everything by a value, for example 0.3, and add, for example, a 0.2, so we will get a value that will go from 0.2 to 0.5. Perfect! Now we can add a little bit of boost to our particles. We are going to deactivate two parameters that are true by default on all materials, depth test and depth right, which make the renderer calculate exactly if one object is in front of or behind another. And this step will slightly improve performance. So let's go back to model.js and write depth test false, depth right false. We also add a blending mode to the particles so they become more fluorescent. Blending 3-point additive blending. Okay, now our particles have a beautiful color. What do you think? We just have to start animating them. So, it's vertex shader time. Now let's try to figure out how to move these particles. If we wanted, for example, to move all particles one unit to the right, the most obvious thing that comes to mind is to write position.x plus equal 1 point. But we get an error right away. Can't modify an input position. This is because we cannot modify an attribute that we have imported. But we can create a variable that contains the same value as position. Let's call it pos. Obviously, it will be a type of vec3, and its value will be equal to position. And replace position with pos. We see that nothing has changed and we have no mistakes, but now we can change the x-axis of pos point x plus equal 1.0, and our skull has moved to the right. If we subtract this value, our skull would move to the left. If, on the other hand, we want to scale our entire model to exactly half its size, we just need to multiply pos times 0.5. So if we multiply everything by 0, all particles would have their x, y and z position values equal to 0. I give you another example. If we multiply only the value of pos x by 0, we would get a flat skull. This is because the y and z values of the particles would remain unchanged, while those of the x-axis would be all 0. Conversely, if we multiply it by 2, we get an enlarged skull. Now that we have clarified how addition, subtraction, and multiplication work to move or redimension vectors, we can add a new variable that changes over time. So let's add a new uniform inside the shader material, which is called uTime. U lowercase is always by convention for all the uniforms we write, and its value, for now, will be equal to 0. Now let's move into index.js and add a new clock variable, which is a 3 clock. In the animate function, we can value uTime equal to the past time, write, school, particles material, uniforms, uTime, value equal to clock get elapsed time, which is a clock method that returns a value that increments based on time. Save. We see that in the console we have errors, cannot read property uniforms of undefined. This happens because when the 3JS loop has started, our models have not been loaded yet, and therefore there is no particles material either. To correct this error, we can add a new property inside model.js. This property will tell us if our model is active or not. This point is active equal to false. In the add function, when the model is inserted into the scene, we set this point is active to true. Instead, in the remove function, this is active will be equal to false. Let's go back to index.js. Now we can put a condition to see if our model's call is active. Now the error is gone, but u times uniform is being enhanced with the value of the time that is passing. I also write the same thing for the horse. Now we can use our uTime uniform to start moving the particles. We import the uniform inside the vertex shader. Uniform float uTime because time is a float number. And we begin to move the position x equal to uTime. Okay, it works. Our skull will be moving farther and farther to the right. Bye skull, bye bye. Now, what if we used the same function of uTime? We got a value that will always go from 1 to -1, and for this reason it will oscillate from right to left. And now what if we add the cosine of uTime to the y-axis? We got a value that goes from -1 to 1, so our skull begins to rotate. The same thing for the horse. We can decrease the radius of rotation by multiplying the sine and cosine by a very small number. For example, 0.01. Zooming in fact, we see that all our particles are moving clockwise. We can also give the same rotation to pos z to give a greater sense of depth. Cosine or sine won't make too much difference now. Now all the particles are moving the same way, and instead we want to create a little chaos, a little mess. and we want each particle to have a different rotation value. So what can we do? Obviously, going to add a custom attribute to our geometry. We will need this attribute to give each vertex some random values to change its movements. So just like we did for the position, for particles position, we will write a new float32 array, which will contain random numbers, which we will insert in a new random attribute inside our geometry. Let's create a new particles randomness variable which will be equal to a new float32 array. This array will also contain vector 3 because we want to give random numbers for each position x, y, and z. So, inside the loop, we are going to add values to particles randomness. Here I want to create a number ranging from -1 to 1. We can use math_random, which will return us a number from 0 to 1 that we multiply by 2, so that we have a number ranging from 0 to 2, to which we will subtract 1 in order to have a number ranging from -1 to 1. We write the same thing for y and z. Always remember to insert the index to set the position of each number within the float32 array. Perfect. Now we need to put a new random attribute inside this .particles geometry exactly as we did for position. Again, by convention, we put a lowercase a in front of random just to recognize all the custom attributes we insert into our geometries. And inside the 3 buffer attribute, we'll have particles randomness. And obviously, also here, we say that its item size is 3 because it will contain vector 3. Now let's do a console log of this particles geometry to see if everything is fine. In our buffer attribute, inside attributes, we have a new attribute called arandom, and inside it will have 60,000 different numbers with some values that will randomly go from -1 to 1. Great! We can now import this new attribute into Vertex Shader. And of course, this time we need to import it. Attribute vec3 arandom. We can use these values of arandom to vary the time of each pose x, y, and z. So, if we multiply the time by this value, we get different results for each position, and the rotation movements will all be different. We multiply u time by arandom.x, y, and z. And let's take a closer look at what is happening. Now, every single particle is moving differently than the others, thanks to the arandom attribute. Since they move too slowly for my pleasure, I create a new time variable that increases the speed of time. Float time equal u time times 4 point. And replace all u time with time. Much better, right? In a few steps, we were able to create a lot of particles that move within our shape. Now we are missing one thing to complete everything. We need to create a beautiful transition from skull to horse. And for this, we get help from the fantastic GZAP web animation library. I think GZAP doesn't need too many introductions. Why do I want to use GZAP? Because hardly in every project that I manage every day, I speak for myself, I use this framework. And unless you're a JavaScript-only animation wizard, this library might be for you. So, since I've already installed the GZAP module for you, we can import it into Model.js. Import GZAP from GZAP. But first, let's go back to Vertex Shader. As we have seen, if we multiply the position by 0.5, we have a scale of the object by itself. If we multiply by 0.1, it will be smaller and smaller until it reaches 0, where it will disappear. So we can use a variable that will go from 1 to 0 to scale the object and animate its value via GZAP when we add or remove particles. Let's create a new uniform that we will call uScale. Model.js and add this new uScale uniform with an initial value of 0. And import the new uniform into Vertex Shader. Uniform float, because it will be a float number, uScale. And let's multiply all the particles by uScale. Obviously, uScale, having an initial value set to 0, will ensure that all our particles are at 0. Now we can go back to Model.js and let's go to the add method. Each time we click on the button, we will animate our uniform from 0 to 1. And to do this, we just need to write GZAP to this particles material, uniforms uScale, open an object, value 1, and save. And let's see this animation. Obviously, it only does this animation once, because we have to reset the value of uScale to 0 when we remove the particles. So let's go to remove and write the same thing we wrote on adds function. But with value equal to 0. Almost perfect. In fact, we want our particles to be removed only at the end of the animation. So, thanks to the onComplete callback that GZAP gives us at the end of the animation, we can move the particle removal and it is active once the value of uScale has reached 0. So, onComplete, arrow function, let's cut these rules and paste them here. Now, by clicking on the buttons, we have a perfect animation of the entry and exit of the two models. However, we are still not satisfied with this type of animation. Let's create some chaos. Go back to Vertex Shader and just work on the x-axis positions for a second. Pos.x times equal uScale. To move the vertices in an elegant way, we could add the sine or cosine of other values to each position, such as the y-axis values, and then we write pos.x times equal u-scale plus sin of pos.y. We are beginning to have a particular shape. This is because the y-axis has a value that goes more or less from 1 to -1, and consequently its sign will have values that will change. And by adding these values to the current position of the x-axis, they will move the vertices in a sinuous way. If we multiply the value of pos y by a number, we would increase the phase of what is called a sinusoidal function. I'll explain better. We multiply pos y by 4. Something stranger here. Try to play with numbers. Now, if we had the time to this operation, we are going to create a kind of dance. Let's try. We add plus time inside the sine function. Oh yes, very well. Now we can do it for all other positions as well. We can modify the y-axis using the sign of the z-axis, for example. Very good. And for a little change, we can put the cosine instead of the sine and play with the parameters as you wish. We also do the same thing for pos z, but inside the sine function I put pos x. Very interesting. Now, if we multiply these three functions by 0, we would always get a value equal to 0. Because obviously, if we add a 0 to a number, we get the same number, and so we would have our original form. In fact, clicking on our buttons, we would have everything like before. So, what if we wanted to animate our functions only during the transition? We just need to replace 0 with a number that goes from 1 to 0. So we can take advantage of u-scale, which actually goes from 0 to 1. But we just need to subtract 1 from u-scale to get a value ranging from 1 to 0. In fact, 1 minus 0 is equal to 1, and 1 minus 1 is equal to 0. So our dance will only happen during the transition. Now we can replace 0 with 1 minus u-scale for all three positions. Perfect, we are almost there. What happens now? When u-scale is 0, 1 minus u-scale will be 1. We would have the particles in position 0, but the sinusoidal function will still be added to their position, and therefore they would not be at 0 anyway. I'll show you better. Let's comment this and look only pos x. When u-scale will be equal to 0, we got pos z times 0, and the function will be multiplied by 1 minus 0, so 1. That's why the particles are still dancing. So what can we do? We can of course re-multiply everything for u-scale, which obviously will go from 1 to 0 in order to bring everything back to 0. Everything is clear? Let's go back, and now we just need to add pos times equal u-scale. Save, and finally we have a better animation. Now we just have to match the time of gzip for the add and remove function. Let's add a nice easing to the entry of the particles. Let's increase its speed a little, and as is, we put a power 3 out, so we have a smoother transition. Very well. Let's write the same thing into the remove animation. Now, to mix all the particles, we just need to delay the entry animation. Delay 0.3. Now, in fact, the model will have to wait 0.3 seconds before entering, and it looks like the particles are blending together. Very good. From here, you have all the possibilities to do what you want. For example, you could give more emphasis to the models as they enter or leave. See it together in the next chapter. We could give more emphasis to the models as they enter or leave. We could add a rotation on the y-axis of the whole model using gzip. Let's write gzip from to, because we want to start from a rotation of 180 degrees and arrive at 0 degrees. So, initially, y will be equal to math pi, which is 180 degrees. Then we add a new object to declare the arrival of the y. It would be the 2 of the from to function, where y will be equal to 0. We also add a duration and is equal to the previous values. We do the same thing on remove. Since the model will already have a rotation of 0 on the y-axis when it enters, we just need to rotate it 180 degrees to get it out, and so, instead of using gzip from to, we'll just use gzip to. Y math p, duration 0.8, is power 3 out. Perfect. Now our animations are more fun. Play around with the parameters to create something crazy. Another thing, if we click on horse twice, obviously, the from to will always start the particles from 180 degrees to get them to 0. So let it do the rotation animation only if this is active equal false. So we write, if not this active, then start the animation. And obviously we move this is active after this condition. Let's save, and now see that when we click twice on the same button, we will no longer have the rotation. It will only rotate when we only move from one model to another. Very well, you now have all the credentials to do any kind of particle animation. You can get crazy. For example, we can change the background color at each change. We can directly pass the background color we want to the model inside index.js. So, as we did it for the colors, we could add a background to each instance. We could add colors that are chromatically beautiful to the colors we have chosen for the particles. I had already highlighted the two colors that looked good. For the school, background 47001b, and for horse, background 110047. So we can add this background equal to obj background inside model.js. Again, thanks to gzap, in the add function always inside the if not this is active condition, let's write gzap to body and change its background color, which will be equal to this background. We always leave its duration at 0.8, save, and we see that now clicking on the buttons will also change the color of the body. Very beautiful, right? We may already end up here, but if you have another 5 minutes, we can add one last interaction to the scene. For example, we could put an animation on the mouse move to rotate around the scene. We will eliminate orbit controls, in fact, because we don't want our user to drag on the page to rotate our particles. So we can go to the index.js and add a new add event listener to the window, which will listen to the mouse move. Let's create a new mouse move block. Window, add event listener mouse move, which will start a new function that we call onMouseMove. This onMouseMove function obviously has an event parameter that is passed to us by the add event listener. Call it he, and let's see it in the console. Now, moving with the mouse inside the window, we see that we have these two values, client X and client Y, that are changing depending on where the mouse is positioned inside the window. Now, I want to use the X value ranging from 0 to the window width to map the rotation of the scene to the Y-axis. So when we move to the left, the rotation of the y-axis of the scene will be rotated to the right. On the contrary, when we move the mouse towards the ends of the window, our scene will be rotated to the left. To do this, we can use a mapRange function that will transform the mouse values, which will go from 0 to the width of the window, into two values that I will use to rotate the scene. There is a mapRange function already inside the gzap utils. Let's find it. Here it is. As you can see, this function accepts 5 parameters. In min is the minimum value of the initial range that we want to map. In max is the maximum value of the initial range. Outmin is the minimum value we want as an output. Outmax is the maximum value we want as an output. Finally, the value we will need to map, and the function will return us a number which will be a range between outmin and outmax. Let's go back to index.js and import gzap. And let's go back on the mouse move function. So we said xmouse will be equal to eClientX and that ymouse will be equal to client Y. Now we can create a gzap2 function to rotate the scene, depending on the position of the mouse. gzap2 scene rotation. We want y to be the output value of the mapRange function. The first value will be the minimum mouse value, then 0. The second parameter will be the maximum value of the mouse, therefore the width of the window. The value we want to shoot the scene when the mouse is at 0, let's put 0.2, and minus 0.2 when x will be equal to window inner width. As a last parameter, we obviously want to listen to the x of the mouse, so x. Save. And now, by moving the mouse left and right, we are rotating the whole scene. Very well. Obviously, we can do the same thing for the mouse Y by rotating the scene on the x-axis. So we'll write the same thing, just changing the parameters, where instead of window inner width, there will be window inner height. And as input range, we will have Y to listen to the Y of the mouse. Now, by moving the mouse over the full window, we have an excellent integration with the scene. Last thing we have to do, and then I swear we are done, it is to disable orbit controls. So in index.js we write controls.enabled equal false. Finish. Guys, I really have nothing more to tell you. We have finished. See you for final greetings. The tools we acknowledge are the key to enter a whole new world, to explore and revolutionize. You can use all the potential of Blender to import 3D objects inside 3JS projects and transform them into a deeper experience. Now you have the basis to allow your creativity to roam free along brand new landscapes, playing limitlessly with transitions, algorithms, colors and models. The only rule you should follow is to have lots of fun, so that studying will never be a burden, especially when you realize you're in such a big universe that the more you explore, the more you realize you don't know.